Okay, so let's go back to, I guess I've got to stop sharing and reshare. And this and this. Okay, so I think this is working. Do you all see this?
We see it good.
Yes, we can
loud
see
and clear.
Okay, so a couple of weeks ago, we were asked to come up with a presentation, and we deliberated for a while which direction we should take. And I really would wanted to do something that was not PFAS. So those of you who have heard 100 of those lately, I think we came up with something that'll be really interesting for you and relevant. There's still a lot of hydrocarbon contamination that we have to clean up throughout the DoD. And this is one of the areas that I think really is less dealt with. So what we're going to do here is I decided to put this together in in three sections. The first is more of a simplistic overview, so you kind of get a visual feel for how the technology works. And then Andrew is going to go into a more detailed overview of the technology, what it does, what it's best for, and then we'll have a specific project example from Kai, who will go through how the process actually works. So, by way of background, remediation of contaminated sites technology is generally well known in most areas. If you have soil contamination, you excavate and dispose of it, or you do soil vapor extraction. Groundwater, probably most of you have heard of pump and treat, or in situ techniques. This is where you would put nutrients into the water, and the natural processes will break down the hydrocarbons along with the nutrients that you introduced. Monitored natural attenuation is also very similar to that, where the natural processes that are already going on in the aquifer tend to break down the hydrocarbons. Bedrock, on the other hand, is a little bit different. If you have solvents that have gotten into the bedrock, as you might expect, you can't pump it off. You can't expose it and use a shop vac on it. You can't really suck the solvents off. Excavation of bedrock, of course, is difficult. So, the primary alternative is basically, well, if you heat it enough, you should be able to vaporize the volatile organics. And that, in fact, is typically how it's done. There are three main processes that are used to remove the solvent. First of all is steam. Now, what you want to picture, and you'll see this better in some of the later slides, but you would drill holes into the bedrock and you would introduce steam. The steam pushes down into the bedrock, pushes outward radially, and follows any of the fractures in the rock. And the fractures then make it easier to vacuum up the vapor at the other end as it comes out. So in essence, the steam liberates the vapor, it mixes with the water vapor, and the extraction wells vacuum up that vapor. Now, there is a small downside to this. The fractures in bedrock are sometimes tricky. You can't be sure that you followed all of the fractures, so great care needs to be taken both in the initial phase and later on to ensure that steam, when it cools, becomes liquid again, and there is the potential that this condensate can follow through the fractures around your vacuum barrier. And for that reason, we'll put up monitoring wells at the outside edges just to ensure that nothing escapes. By way of energy cost, as you might be able to visualize, water vapor, of course, is heavier than hot air, so the energy consumption is slightly higher than for the hot air method, which is our next method. Hot air works very similar. Again, it's the heat in the hot air that releases the solvent and volatilizes the vapor. And the extraction wells vacuum the vapor as with steam. Once again, you have a physical force that's pushing the vapor radially through the fractures, which make it easier to recover. And of course, being hot air, it doesn't have any vapor, it doesn't have any water vapor, so there isn't any condensate to worry about. The third type is heating rods. I was actually hoping to show you this, but under COVID conditions, we weren't able to do this. But in essence, it's very similar. You would just simply take a heating rod, visually in similar nature, like the kind that you use for your hot water heater, and you would stick that into the hole. Now, in this case, the mechanism is solely heat. So it acts more on the immediate vicinity than it does on the fractures. So it's limited to what escapes the matrix through natural pathways and what can be extracted by vacuum wells. Since you don't have this force of hot air or steam to push the contaminants out, you need more wells, both where the heat goes in and extraction wells where it goes out. It doesn't take as good of advantage of the fracture pathways. However, of course, since it's only heat, there is no condensate. So what I next wanted to do, and those of you who know me well, this is a pretty common thing for me. I wanted to take a look at, okay, how can I visualize this? How can I see how the process really works to kind of validate the things that you know from literature? So one of our employees had a core of sandstone, which he borrowed me to experiment on. The first thing that I did is I added lighter fluid, which is, similar to the kind of things that you might imagine can get into the ground. Some of it did slowly soak into the pore matrix, which is kind of what you'd expect. The majority followed then the fractures. Now, the next part wasn't strictly necessary, but being the kind of guy that I am, seeing all of that lighter fluid on top of that core of sandstone, I couldn't resist. I had to see what would happen if I lit it up. So as you can see, it made a rather merry blaze. It really lit up very nicely. One of the interesting things that happened, though, is when it had all burned off and the flame was out, it continued to release vapors. So for about 5-10 minutes afterwards, you could still see the little wisps of vapor coming off of the core. This is basically because the flames had heated up the exterior of the core enough that you still had very hot rocks on the outside, and that allowed the vapor that was in the pores to be released. Okay, so the next thing is did a little research, and the vaporization temperature of lighter fluid requires about 85 degrees. Now, important here, to know what temperature you need to heat to, you need to know what contaminants are present. 85 just happens to be the one for the lighter fluid that I used, but depending on what your contamination is, that's what drives how hot you need to get the rocks to. For simplicity's sake, I just put the sandstone core into the oven. My wife wasn't terribly pleased, but she understood. And as you can expect, and I hope that you can see this, you can see that the vapors are actually coming off the rock as the hot rock volatilizes the vapors. So with that in mind, heat should work. So then the next question is, well, if you only heat it, how do you recover it? And as I said before, the steam follows the fractures And so the fractures heat up first, and the steam follows the pathway that the contaminants took. So let's take a quick look at that. So as you should be able to see here, I shot steam through the core, and the steam follows the hole in the center of the core through the fractures in the brick, and you can see how the steam reaches that area first. It did, however, also reach the core, and we'll go to this next, and this is the basic data that we had. So by introducing steam, you can see by the yellow line, the fracture areas heated up first. There was a quick jump to 50 degrees within the first 5 minutes, and thereafter, both the core and the fracture heated up pretty much linearly. After the steam was removed, another interesting thing is the core continued to go up in temperature thereafter before falling off after about 5 minutes. So in essence, what's happening is the heat that's at the center of the core continues to radiate outward for a little while. Now, this is something that we actually take advantage of during the thermal remediation. So you'll have periods where you heat up the core or the bedrock, and then you'll have periods where you let it settle for a little while and let the heat dissipate. As you can also see here, the cooling is roughly linear. So it takes a considerable amount of time for the rocks to cool. What was also very interesting is it took roughly an hour to reach the 85 degrees. And so what I wanted you to visualize out of that, you saw the size of the core that we were looking at. And this is a very small, maybe 6-inch core. And so it took roughly an hour for that little core to reach 85 degrees. So if you expand that to a whole area of bedrock, which is considerably larger, you can kind of visualize the level of energy that is required in order to heat up the rock. And so it requires a lot of energy, but as we'll get to a little bit later, it's also a much quicker remediation process than many of the other processes. So with that, I'll pass it over to Andrew, and we'll take a deeper look at the hydrocarbon contamination theory.
Hi, everyone. So how does the technology work? As Michael explained, heat is applied to the soil or bedrock using 3 different methods. And this is usually with vertical boreholes, but you can use angled boreholes to get under buildings too, if it's a tricky access site. So increasing the temperature converts the volatile compounds to a gas. And importantly, in the gas phase, a massive solvent occupies a much larger volume than it does as a liquid. So that's an important point, that pushes away. There's already an expansion to make the extraction an easier process. A vapor extraction system is installed in the boreholes to remove the volatiles from the gas phase. And the depth of that extraction system can target the contamination that we've identified through different site investigations. The extracted vapor is there, and liquids are then treated in above ground filter systems in carbon beds, and monitoring the temperature and the volatile gases during the remediation works is important to check the progress over time. So detailed soil and groundwater investigations are very important to make sure we have a good understanding of the impacts both vertically and horizontally, because we want to minimise how much remediation is required and obviously the related costs. So we need to have a 3D picture of how the contamination got into the ground or the groundwater as best we can, because that will then determine how it can be removed. Groundwater extraction may also be required to capture the mobilised contaminants during the remediation works. So we need a good understanding of the groundwater conditions to minimise how much groundwater needs to be removed and treated. Next slide. Next slide, Michael. Yep. So what are the advantages of the technology? It's good that no excavation or transport of soil is required, so it's suitable for areas near buildings or on active sites. This can be very important for some clients with very busy active sites where traffic movement can't be disrupted, etc. It's also good because no waste is created from excavation works, which can be very costly to remove off-site. Sustainability is always a key issue when we assess the different technologies to gauge what the carbon footprint will be from the selected technology. Another advantage is shorter remediation timeframes, so less disruption to site operations is important, and less traffic movements from the project team is obviously a smaller carbon footprint as well. And compared to other methods, it's less sensitive to different soil types or bedrock. And the disadvantages, it is expensive compared to other technologies because of the high energy demand. Soil or rock is not a good conductor of heat, so a lot of energy is required to power the heating system. Soils can shrink from the works from the heating, so there can be potential structural issues next to buildings. But this can be addressed by injecting water vapour. The works can also liberate vapours possibly into indoor building areas, internal spaces. So sizing and control of the extraction system is required, and obviously regular air monitoring as you do the work. And the method is more it needs more intensive monitoring and supervision because it's a shorter remediation phase. So more coordination of the works is required. Next slide, thanks. So this cross section shows a typical system with the blue color in the middle shows the contamination in the unsaturated zone and just below the groundwater. The groundwater is the blue line, horizontal blue line through the middle. And then the red injection wells are on the left and right. So the pink colour is steam pushing outwards from the two wells and mobilising the volatiles in the ground. And then the darker red colour is the condensed hot water as the steam cools and moves away from the injection well. So it's showing a push-pull effect by the extraction and the steam injection works. The next slide just shows that in a bit more detail, with the green area showing the contamination being drawn towards the extraction well, which is on the right, and then the red heat fronts are on the left, pushing outwards and mobilising the volatiles. That also shows the groundwater system lower down. So the benefit of thermal is that it's heating the unsaturated soil above groundwater and also the ground within below groundwater level. So that's another advantage of this technology. A lot of technologies won't do that. Next slide, thanks. This shows a typical layout for a treatment system. So at the bottom it shows the network of injection or extraction wells together. Focused on the source area, and then the vapour being drawn from that area is taken to a vapour treatment system through carbon beds, filter systems to clean the air with a control trailer on the top right, where all the control systems and monitoring equipment would be, and often a different power system top left is required to provide the additional power this technology needs. Next slide. So typical remediation objectives that we need to address with these technologies is usually about protecting groundwater drinking resources, obviously, and sensitive ecosystems. but it can also be to address some possible impacts to human health if there's an occupied building in the area as well. Contaminant source removal to minimise future impacts to the groundwater system. Often these solvents stay in the ground for a long time and they just slowly bleed into the groundwater system. So it can take decades. It can impact the groundwater over a long time frame. An important concept when selecting the best technology is the concept of remediation to the extent practicable. So we look at a range of factors: technical feasibility, long-term effectiveness, remediation timeframe, cost, and obviously the carbon footprint or sustainability is an important issue as well. So the goal isn't to remediate everything, but to consider the limitations of the technologies as well. So after the mass is reduced from these remediation works, the natural process of degradation can occur, which will further reduce the impacts to groundwater over time. And also at lower contaminant concentrations, microbes, which are already naturally occurring in the geology, can further break down compounds to further clean up groundwater. Next slide. So typical monitoring or validation requirements includes the following. So during the remediation works, as I said, you do your monitoring at neighbouring wells to check the progress of the works, to make sure you have a good control of the system, and that you have good real-time feedbacks as the works progress. Monitoring of groundwater levels at nearby wells to confirm that you do have good hydraulic control. So this checks that the groundwater is being captured properly during the remediation works. And then after remediation, we usually do soil sampling within the treated area to confirm that the works have been successful. So has the size of the source been reduced? Have the remediation objectives been achieved? And then in the longer term, we continue to do groundwater sampling to confirm that the groundwater impacts are improving over time. So now it's over to Kai with some details on a AECOM project.
Yes, hello everybody. I'm going to present actual site where we will conducting an in situ thermal remediation this year. The site is located in a forested area on an army installation. You see the site on the upper right portion of the picture. It's a storage area for military equipment, and we assume that the chlorinated solvents were once released during degreasing activities at the site. The release area, Michael, if you tip on the slide, yes, the release area is shown in red, and also the dashed line shows the remediation area. Groundwater flow is towards southwest, and you also see on the picture the circles represent monitoring wells, and the colors represent the different CHC compounds and the concentrations. The site is underlain by about 2 meters of unconsolidated soil, followed by sandstone. And the picture that you see on the right side is taken from a televiewer survey. So it shows a borehole wall of one of the monitoring wells located down gradient of the remediation area. And you see on the picture the upper portion, that's just the steel casing, that's not the bedrock yet. So the bedrock is actually the red portion underneath, starting at about 2 meters something. And I'm not sure whether you can see that, but there is a black line just underneath 2.5 meters. This is an open bedding plane. And open bedding planes are always like potential pathways for contamination. And you don't see any vertical fractures here. They are present, but on this picture you don't see it. It's often you don't see this on any surveys. But yeah, the purpose of these televiewer surveys is to get an idea about the structure and the preferential pathways. So the pathways are important because those will be primarily targeted by our steam injection. So if you move on to the next slide, in order to define reasonable remediation goals, we first sat down with the client and the authorities, and the remediation goals were: first, we had to remove the contaminated soils, and the remediation target for the contaminated soils was 1 milligram per kilogram. Then, of course, the thermal treatment of the unsaturated bedrock in order to interrupt the contaminant transport from the unsaturated bedrock into the groundwater. This pathway was identified as a major pathway and as a major threat to groundwater. We had identified residual contamination in the unconsolidated soil and in the bedrock, and just by infiltrating rainwater, I mean, this contaminants get in solution and are washed down into the groundwater. So this is important for us to interrupt this pathway. And how do we define when do we end our remediation? And we will define this by this recovery curve. You see the little graph on the bottom, and it's an example of an asymptotic recovery curve, and the upper line represents the recovered mass in kilogram over time. And towards the end of the remediation, the mass recovery slowly declines, and this is shown by the flattening of the curve. And this is called like the point of diminishing returns, and this would be like a sign for us that the remediation is coming towards an end. Initially, there was also a goal defined for the bedrock of 1 milligram per kilogram, but this is no longer enforced. And I think anybody who's familiar with bedrock knows that this would be difficult to achieve and also to prove that we actually meet this goal, because once you take samples from the bedrock, and I mean, you would need to grind it in order to analyze the samples, and all the volatiles would be lost. So our goal is strictly, we operate the system as long as it's reasonable and as long as we get significant contaminant mass out of the bedrock. So we can move to the next slide. On this picture, you can see the remediation area and boring locations. We drilled 12 borings along 4 transects to the top of the water table. And at each of these borings, that are the black dots here on the area, each represents 1 boring. At each of these borings, soil vapor samples were collected, and we also collected a water sample from the top of the water table, which is at a depth of about 11 meters. At each of these borings, also a geophysical borehole survey was conducted to identify the location of the bedding planes and also fractures. And the goal of these, or the purpose of these borings, was to better delineate the impact in the bedrock and to identify the most contaminated areas, because these are the areas that we focus on during our remediation. And on the next slide, you see a cross-section. You see on the cross-section, on the upper portion, you see the former release area and about the unconsolidated overburden soil on top of the bedrock. And as I mentioned, the contaminated soil was removed during an initial step. And we estimated that during removal of the unconsolidated soil, approximately already 100 kilograms of CHC was removed. Also, a pilot test was conducted in the former release area to get more data to design the final system. The top of the bedrock is also the first pathway for infiltrating rainwater. Michael, if you click on it, it shows like the first layer on top of the bedding plane. So once rainwater goes through the unconsolidated soil, it accumulates on top of the bedrock and is flushed. You see that it's a little bit sloping towards these wells on the left side. And then, of course, we've got vertical fractures also. If you click on the slide again, you see that groundwater also infiltrates further downward along these vertical fractures. And then we've got a first bedding plane at 6 meters, and also water can accumulate on top of the bedding plane and then is flushed downward towards our monitoring wells. Then if you click on it again, this would be our second bedding plane at 10 meters. And below our second bedding plane, you see the water table at about 11 meters. Also shown here on the picture, on the cross-section, are the results of the soil vapor sampling. You see that the portion above the first bedding plane, we had quite a moderate concentrations of 40 milligram per cubic meters, which is not very much. The deeper portion shows a significant higher concentrations at in certain areas, and the threshold for remediation in Rheinland-Pfalz is usually something about 40 milligrams per cubic meter. So, of course, this has an important information on how to design the actual system. Okay, let's take a look at the next slide. Okay, this is that shows This is a sketch. It's a preliminary layout on. You see the remediation area. The red circles are the injection wells, and the blue circles are the extraction wells. Each well has got different screen sections at different depth intervals. So some wells have got 2 sections or 3 sections. One may have only 1 screen. And what's important here is that you have hydraulic control over the site in order to avoid that mobilized contaminants are escaping the site. So therefore, the entire site is surrounded by extraction wells, so the blue ones, and each injection well is surrounded by extraction wells. So this is just an example. It's a preliminary sketch, and the actual layout will be slightly modified for the site. So we can move to the next slide. During the remediation, groundwater samples are collected at our monitoring wells located down gradients of our remediation area, and samples will be collected and analyzed. And if we see an increase in concentration at these wells, and then the concentrations may reach a defined threshold value, then we need to operate extraction wells. So this is a safety measure. As I explained, mentioned before, this is, we tried to keep hydraulic control during our remediation with our extraction wells within the remediation area, but in case we cannot fully capture everything, the extraction wells at the down gradient portion kick in and so prevent that any dissolved contaminants are leaving the site. And on this slide, you see it's a simple model. The lines with the little arrows that represent the flow lines, and you see that all the flow lines coming from the remediation are captured by the extraction wells. So we've got the conclusions. So in situ thermal remediation, it's suitable for addressing all volatile contaminants, particularly hydrocarbons. It's typically faster than any other methods used to address volatile contaminants. But the disadvantage is it's very energy intensive. And so we've got high energy costs. It works in places that other methods do not. So this is important for active or limited access sites. And it can be a solution in bedrock and below groundwater, where other options are not suitable. And regarding the disadvantage, since we've got facing very high energy costs, typically these sites, the remediation duration is very short. So we anticipate for our site, for example, that the in situ remediation should be finished in less than 6 months. Thank you.
Okay. So any questions from anyone for this presentation?
So, and we'd encourage anybody raise your hands if on the screen if you have a question. And I have a couple questions. So first, I'd like to say thank you very much to Michael and Andrew and Kai for taking the time to put this really interesting presentation together. It really was interesting and certainly appropriate to the wide spectrum of audience that's listening today. So I do see that Charisse has raised her hand. Do you have a question, Charisse?
I do. I have a quick question. You might have covered it and I missed it, but with the thermal heating, how long does it take, typically, depending on the method you use, for the bedrock or the soil to come back to ambient temperature?
Kai, you got a feeling on that one?
I might have to go back to our pilot test, but it may take several days. You see that after shutting down the system, during our steam injection, we also have these extraction wells, and you see that after the steam injection stops, there's a continuous mobilization of contaminants, and so it takes several times until it cools off to ambient temperature, I would say.
Thank you.
Now, Michael, if you want, you could take off, release control of the screen, and then maybe the three of you or whoever can turn on their camera while we're answering questions.
Okay.
Just to make us all feel a little bit more like together.
Okay, so I hope that was successful. Yeah,
it works good. Okay. And I see Kai. And I see Michael. Great, thank you. So so I got a couple of questions too. Oh, somebody else is, I want to let everybody else have a chance. Let's see who raised their hand there. Let's see. Oh, I guess it went away. Okay. So I have some questions. So where are you mostly applying these techniques today? I know you gave us one example on an Army base, but is this kind of like something you're doing regularly or just emerging, or what? Is there a lot of demand for this process in Europe?
Yeah, well, I mean, within Europe, I know that we have some good knowledge in the UK. I guess they're not Europe anymore, where they have some project work that they're doing. But we do have, Kai, a couple of sites here in Germany that we're doing.
We have one site, I know from our colleagues in Essen, they are planning an in situ thermal remediation, which hasn't started yet. but I'm not aware of any other sites, so it's not a very common technique.
And is that because it's relatively new or because of the expense that you've pointed out, or you don't know?
It's, I mean, the expenses, of course, I mean, you have to have a good site knowledge, and I mean, it does not apply. I mean, there are other methods that are sometimes more suitable. There's a wide, I mean, variety of options that you have. And I think many clients may just, yeah, say, okay, this looks very expensive or so, but at the same time, if you do calculations how long you would need to operate a hydraulic containment system, these techniques become more attractive. Yeah, if you take it in the look over a longer time span. But I'm not quite sure why it's not more often applied. I mean, this is we recommended this method for this site, for the Army site, and for the site in close to Essen, and for other sites, yeah, I mean, it's always an evaluation. There are many techniques available.
Great, thank you. And I see there's a hand raised, but I'm going to go first to the question that was posted earlier. This is from, excuse me, Arnold Blanton. And he's asking, what about the microbes that are in the soil? How quickly do they come back into the soil or bedrock? And are there any requirements for monitoring it after the contaminant is removed?
There are no requirements, and we did not monitor the microbes. And of course, it will have an effect, but we never really, put too much. It has never been really analyzed. I think I'm not quite sure whether it has been ever, Michael, analyzed. I mean, of course, the microbes will not like the high temperatures. That's for sure. Yeah.
Sure.
And considering those temperatures, I mean, as a water engineer, I mean, if you're talking about 60 degrees or more, it pretty much kills everything. And so you can expect everything is going to be dead. On the other hand, as soon as you have rainwater, as soon as you have any of the microbes that are in the highest level, it's reintroduced from runoff. And so, while the microbes themselves that had been in the area would die off, it refreshes fairly quickly. And I can say from my water work in Africa, actually it is very quickly after a rainfall event, you get quite a bit of microbes that re-enter the area.
Interesting. Okay, and Steve Cater, you've raised your hand. Go ahead and feel free to turn your camera on if you want and ask your question.
Hi, I'm sorry, my system kicked off in the middle and I got it back on just in time to hear Kai say that this would apply below the groundwater line. I expected this only to work in the VADOS zone because the energy cost would go up drastically when you hit the groundwater. Can I ask for a 1 minute refresher course on the effect below the groundwater line? Thanks.
Steve, first of all, I would say you are right. It's more suitable in unsaturated bedrock, and I mean there are sites where it has been successfully done below the groundwater. And I'm not quite sure. I haven't done any in situ thermal remediation below the groundwater, but I'm not quite sure whether our colleague Martina is here, whether she can. Martina, are you?
Yeah, I saw that she was in, and if she does not can't get in, I would also like to address that a little bit while she's trying to work in that. One of the important factors in the choice of technology is the overall picture. So in other words, you may have a site where you have contaminated bedrock and contaminated groundwater, whereby it's, the other methods aren't necessarily suitable for the bedrock portion, and since you also have it in the groundwater, it's as a combination a useful method to do so, whereas it would be less likely to be useful if you're only talking about thermal remediation within the groundwater. So did we get Martina?
Yes, I'm here. Sorry. I I need to say I also didn't make a project where below the groundwater, but it is possible. You have a slightly different steam distribution below the groundwater because of the groundwater pressure. But it's possible to make it. And yes, you have a little bit more energy input. It's higher, but it would be possible because you are vaporizing the groundwater and your solvents together, and then you can extract it as steam.
You can also deliberately lower the groundwater table with extraction works, so that you have a greater area of unsaturated zone to do these work from. So yeah, that's an option as well.
Okay, and I saw there was a message.
Margaret, you're on mute.
Oh, sorry, I was on mute, sorry. Yes, Gorm Heron has asked a question saying there has been approximately 600 in situ thermal projects worldwide. Oh, okay, so not a question, but a statement. So that's quite a bit. They'll be interested. Gorm, do you know, I mean, can you tell us more about that? Where are they using it more often?
Yes, can you hear me?
Yes.
Okay. Yeah, there was a paper recently by Horst and others, John Horst from Arcadis and some co-authors about a month ago that is a very good source of this. It has maps of the world that shows where all the projects have been. It has analysis of which methods have been used and what geologies they were used in. And that's just very informative. Too much information to share on a call like this, right? But yes, probably half of all those projects were in the US, and then the other half has been across the world, right? And just in Denmark, which was an early adopter of thermal remediation, there's been more than 15 full-scale treatments. Not all of them into the bedrock, the chalk that's typically under Denmark, but quite a few thermal projects, mostly for chlorinated solvents, that are basically saving some of the water abstraction wells so they don't have to close them down, and also remediating under houses and so on.
Very interesting. Thank you. And I have a question too. I mean, I admit I personally don't have a lot of background in remediation. So one of the things I was wondering about is you were, Kai, when you were giving your example, you talked about the 40 milligrams per cubic meter of standard for the contamination. And I'm wondering just how correct or appropriate are those standards that we're using? And I mean, are they getting checked or rechecked or validated on a regular basis?
You're on mute.
Sorry. So it's a guideline, and each site is different. And of course, you have to make a risk assessment and look at the entire contaminant mass and what kind of contaminant mass flux you have. You can do this by simple calculations and estimate, like, for example, 40 milligrams of cubic meter equals this concentration in infiltrating, so in water that infiltrates this source zone. So you get an idea of how much contaminant mass is actually entering the water table. So if you've got only a small site and the mass flux would be very small, so there would be no need to remediate it. But if these concentrations over a larger area, you will have a significant contaminant mass transfer into the groundwater. So it's a site-specific evaluation. So it's not, and it's always you have to negotiate it with the authorities. Yeah, and you usually, I mean, we have many sites where we would not recommend anything because even if there are small locations and exceedance, it should not automatically trigger any remediation work. So you have to balance it. I mean, it's a site-specific decision.
So it's really more of an art, and those are guidelines, and then
it makes it more interesting. So each site is different. So it's yeah.
Yeah, very interesting. And I had another question too, another very basic question. Really is, like so many other things, of course, some prevention of this is more important in the first place, right? But the tank that you had used in your example on the military base, that was an underground tank, right? Is that correct?
No, I mean the release. You mean the release of solvent at the
tank itself? The solvent is stored.
No, it was. We think that the solvents were used during degreasing activities. So it was a storage area for military equipment, and I mean usually for cleaning purposes they use these chlorinated solvents. And I know, like from the history back in whatever in 60s, and so I mean nobody thought about it that it would have any effect on the on the environment. And the recommendation was, if there's leftover chlorinated solvents, you can just dump it onto the ground. And there was I mean, they used it basically everywhere for degreasing purposes. And so this is one of the most common contaminants currently, and unfortunately it's also quite persistent, and some of the degradation products are more toxic than the parent compounds. And on this particular site also we are upgradient of drinking water wells, so this is a sensitive site. But it was used for degreasing purposes, cleaning purposes on the storage area, so the spill occurred at the surface.
I see. I guess I had thought it was from a leaking tank, but it was from activities. That makes complete sense. So another question I had that makes me think about is, are these contaminations, are we actively going out to areas where that we know that those activities were taking place over time and looking for the contamination, or is this more as it's encountered because of other things?
No, I mean, usually you do like a historical review, and of course you identify those areas where these chemicals were used. So, I mean, we know, for example, like laundries, they use chlorinated solvents, or motor pools and wash racks and so on. So these will be all investigated, but for filling stations, of course, you've got other contaminants, but yeah, you look for the trigger sites. Yeah.
Okay, that makes sense. Great. Are there any other questions? Anybody just speak up if there's any other questions. We've got just a couple more minutes. And if not, that was a really great presentation, all of you. I really appreciate you putting this together for all of us and coming on board this morning, this afternoon to present and answer our questions. We wish you lots of luck as you continue conducting this work around and keeping our environment safe for us. Thank you.
Thank you.
Thank you, everyone, for joining us. Thank you.
That very interesting presentation, very fascinating. Thank you so much for doing this. Reminder to everyone, this will be posted, the recording will be posted on the website in case you missed anything. And we hope to see you at our next event. Thank you.
Likewise for
you.
Kaiserslautern. Thank you. Thank you,
Bye.
everyone.
Thank you.
Bye-bye.
Cheers.
Great. Thank you all.